The purpose of today's lesson is to go over a concept called percent yield, which is essentially looking at the efficiency of a chemical reaction with how much you should be able to produce of something based on stoichiometry, and then comparing that to the actual amount that you create in the lab. So usually if we're looking at a percent yield from an experiment standpoint, the 90s are where you want to get. That means you're at like 90% efficiency or above, which is good. So percent yield is a really valuable tool when we're looking at how an experiment went and if we think it went well or maybe not so well. So in order to do this, you have to have two values. You got to know how much you got via the experiment, so what you're actually measuring in your experiment, and then what you should have gotten based off of the stoichiometry that you calculate. So let's say we're looking at this first one. This is kind of our easier of the examples. So the question is asking us to solve for the percent yield if we have 35 grams of NH3 that's reacted. And we're being told that we produce 47.7 grams of our product. So I have these written up here just so they're kind of out of the way. So the way that you determine your percent yield is first you have to look at what the theoretical yield is. How much should you have made? Because we know how much we actually made. That's our 47.7 grams. So the first thing that you're going to do is take the amount of your reactant, so our 35.0 grams of NH3, and what we want to do is convert that into CONH2 using stoichiometry, and that will tell us the amount we should have made based off of the reactants that we have. So you're going to add up your molar mass to go from grams of NH3 into moles of NH3, and when you add up that nitrogen and those three hydrogens, you should get 17.04 grams. And that will cross out. Then you're going to use your mole ratio based on your balanced equation, going from moles of NH3 into moles of your product. And our mole ratio here is going to be a 1:2 ratio. At this point, you can now, again, use stoichiometry to work backwards. So now you're going to be going from moles of CONH2 to and turning this into grams. So you're going to have to add up the carbon, the oxygen, the 2 nitrogens, and the 4 hydrogens, which gives you a molar mass of 60.07 grams. So when you solve this across, what you should find is that 61.7 grams is your theoretical yield. So this is, if everything had worked perfectly in that reaction, this is your theoretical. Okay, so now you're going to use the percent yield formula because we know percent yield is the actual over the theoretical times 100 to get it into a percentage. So your actual amount is what you had created in the lab, that value that was given to you, 47.7 grams. Your theoretical, what you should have made, is 61.7 grams, and your overall percent yield is 77.3%. So what that means is you lost some product somewhere in the mix. It either didn't react fully, maybe you lost it somewhere in the process, like getting it from one beaker to another beaker in a filtration process. There's lots of different reasons why you don't have a better yield than this. It happens, but that is how you would determine the efficiency of your chemical reaction via your lab data. So let's look at a different one, and this is kind of looking at it from a different angle. So this can be a little bit tricky, definitely harder than the first one. And in this case, we're actually given a percent yield. So we're being told in this that we have a reaction that has an 87% yield. So 13% of the product got missed somewhere along the way. We're being asked how many grams of aluminum are needed if we want to produce 25.2 grams of hydrogen. And what we have to remember is we already know this is not 100% efficient. So the thing that we are trying to figure out is how much aluminum that we need, but keeping in mind we have an 87% efficiency. So we need to figure out how much we would actually need with that 13% being lost of it. So we're going to be finding the theoretical here. So I'm going to put that as a note here. So there's actually kind of two methods that you can do for this. So I'm going to show you both, and you can sort of pick whichever one works for you. So method number one is where you're going to be doing the stoichiometry first and then using the percent yield later. So you kind of have two choices. So the first method is using the stoichiometry first. This is what I prefer, but I mean, you can do it either way, you'll get the exact same answer. So if you use the stoichiometry first, you're looking at the amount of hydrogen gas that you're producing. So that's the 25.2 grams. And you want to convert this into the amount of aluminum that would be needed to create this much. So you're going to be going from grams of hydrogen to moles of hydrogen. You add up those two hydrogens, it's 2.02 to 1. You're then going to use your mole ratio to go from moles of hydrogen to moles of aluminum. This is a 2 to 3 ratio. And then you're going to be going from your moles of aluminum into grams of aluminum using aluminum's molar mass, which is 26.98 grams per mole. So at this point, in order to make our 25.2 grams, we would need 224.4 grams of aluminum. But this is not the end of our problem, because we know that we don't have a perfect 100% yield. So we actually need more than this. This is not enough, because this is how much we need once that 13% has been lost somewhere. So what we actually need to do now that we've done this first step is the stoichiometry. Now we need to look at our 87% yield, understanding that that is created with our actual over our theoretical, okay? We also have to keep in mind that a percentage is really just a decimal that's been multiplied by 100. So for easy sake, I'm going to use this as 0.87, so I don't have to go through and divide out 100. So if I'm thinking of this as 0.87 is equal to our actual, which is what we just solved for, so I'll put a little note there, over our theoretical, okay? I'm just going to call this, instead of writing theoretical here, I'm just going to write that as x, just for simplicity, and I'll put theoretical underneath of it. And you want to just solve for x. So rearrange your equation. This now becomes 0.87. X is equal to 224.4. And when you solve for x, you find that this is 258 grams of aluminum that is actually needed. Because again, when we use this stoichiometry up here, this told us how much grams of aluminum is actually going to get used up to make, you know, this grams of hydrogen that we're starting with, but our reaction is not 100% perfect. So we're losing some aluminum, meaning I actually need this much in order to use this much, because we're losing 13% somewhere in the mix there, okay? Your other method of solving this, so that's method one, starting with the stoich. The other method, which is method two, is where you're starting with the percent first, and then you're stoiching after that. I don't know if that's a verb, but you're using stoichiometry after that. So in this kind of setup, you're just working in the other direction. So you know you have 87% yield, which is made up of your actual over your theoretical, and that 25.2 grams of hydrogen is the actual, right? So when we plug this in, 0.87 is equal to 25.2 over x. When you solve for x, you'll find that this is 28.966 grams of hydrogen, and that is your theoretical, right? So now if we use stoichiometry to figure out the amount of aluminum that would be needed to make that, so we have 28.966 grams of hydrogen, and we're just going to use stoichiometry to figure out how much aluminum would be needed to create that. So we're just going to plug in here 2.02 grams of hydrogen per mole. Use our mole ratio to go from moles of hydrogen into moles of aluminum, 2 to 3 ratio. And then we're going from moles of aluminum into grams of aluminum using our molar mass of aluminum and finding, and you multiply this across, 258 grams of aluminum needed. So either of these methods that are shown here, either doing the stoichiometry first and the percent yield second, or using the percent yield first and going backwards to do the stoichiometry, it really doesn't matter, because you see we get the exact same answer each time. So it's really up to you, whichever method kind of makes the most sense to you. You won't find one works better than the other. It's just whatever your preference is. So if you have any other questions, please make sure you let us know.